Alright, so here we're going to start off the same that we ended the last lesson, day 1, power series. But then after we do that, we're going to look at the first and second derivative of this, and then we're also going to look at the integral of this. And so I'll talk more about that when we get there. But let's start off just doing the same thing that we did before. So we want to identify the center. So the center, we look at x, and there's no addition or subtraction, so the center is 0. Then so that's 1. 2 is the ratio test, so we're going to take the limit as n approaches infinity, and we're going to do n plus 1. Now here we talked about this a couple times, the power of -1, and we're taking the absolute value of that, so it's going to make no difference. So we can just disregard that basically. So we add 1 to n here. So n plus 1 plus 1 is going to be n plus 2. Down here we're going to have n plus 1 plus 1, so that's also going to be n plus 2. Multiplying by the reciprocal. So we're going to get that, and then here we're going to have x to the n plus 1. Alright. So looking at these exponents, this exponent is 1 higher than this one, so that'll cancel out all those except for that last one. So that's going to be the absolute value of x, leaving us with the limit as n approaches infinity of n plus 1 over n plus 2. Okay, so as xn, this should be an n. Okay, so we fixed that. That was supposed to be an n. And the limit as n approaches infinity here, that's just going to be 1. So I could put times 1, but I suppose times 1. And then we want to compare that to 1. So if we do that, then we can put -1 and +1. And then we need to test those endpoints to see whether we have parentheses or brackets. So if we let x equal -1, then we have -1 to the n, and then that's -1 to the n plus 1. And then that's all over n plus 1. So if we multiply, one of these is going to be +1 and one of these is going to be -1. That happened to one of our other examples, so that's going to be -1. So we're going to have the sum n equals 0 to infinity of -1 over n plus 1. And that we can do the limit comparison test to 1 over n, which is a p-series. And n equals, the power equals 1, so it diverges. So we know that the -1 is a parenthesis. And if we let x equal +1, then we're going to have -1 to the n, and we're going to have +1 to the n plus 1. So that one to whatever power is going to be 1. So that's not there. So then if we just look at this, 0 to infinity of -1 to the n power, n plus 1, we know that that converges by the alternating series test. Since that converges, that's going to be a bracket. So that's our interval of convergence for the function. Okay, now we're going to do the first derivative. Okay, So if we look at the derivative of this, focusing on the x, that's what we're taking the derivative of. The rest of this is not going to change. So that's going to be n equals 0 to infinity of -1 to the n. So if we take the derivative of this, we bring the exponent down, so that's going to be n plus 1 times, and we subtract 1 from the exponent, so that's just going to be x to the n. And then all of that was over n plus 1. So that's going to cancel out. Now we can just look at this, and that is -1 to the n, x to the n. And so up here it says that for each of all of these things, the interval of convergence will remain the same. The only thing that changes is possibly the endpoints, depending on what happens. So it says when you're differentiating, parentheses remain. So if we go back and look at what we had, the parenthesis for derivatives is going to stay. So that's going to be -1. So all we have to test is the bracket to see if the bracket stays or not. So we're going to let x equal 1, and we would have to infinity, and we would have -1 to the n, and then x would be 1 here. So that would be 1 to the n, which is not going to really have an impact on that. Okay, so this diverges because of the nth term test, because the nth term is not approaching 0. So that means that that's going to become a parenthesis. So that bracket that we had here became a parenthesis here. Okay. Now we're going to look at the second derivative. So the second derivative, we're only doing 2 examples, this one, and we'll do one on the back. So we have -1 to the n. Now we're going to bring the exponent down. We're taking a derivative, so bring the exponent down, times, and then subtract 1 from the exponent there. So the parentheses stay. So that is just going to be the same. So I don't know that we even needed to write down this second derivative of it because parentheses stay. So I'm not enough of an expert to know whether we needed to bother with this or not. But it's still good practice, I suppose, to see what happens to that. Okay, so now if we go back and we integrate the function and see what we get there, that's going to be n equals 0 to infinity, and this stays the same. So to integrate, we go back up to this, we add 1 to the exponent, so that's going to be n plus 2, and we divide by the new exponent. So n plus 1, that's already part of it up here, and then we have to divide by the new exponent. So that's going to be n plus 2 there. Okay, so when we integrate, brackets remain. So if we go back to the original, the bracket's going to be there. So we know that that is what's happening. Now we need to look at -1. Let x equal -1 and check that in here. So that's going to be -1 to the n, -1 to the n plus 2, and here it's going to be n squared plus 3n plus 2. So if we look at that one, that's going to be +1. We multiply that, we add the exponents, that's going to be 2n plus 2, and that's going to be even no matter what. And so since we have -1 to an even power no matter what, that's going to be a +1. And then if we look at this, we have that. So what we can do here is a direct comparison. Okay, and we can compare that to a p-series. So converges by p-series because 2 is greater than 1. So since that converges, then the parenthesis is going to become a bracket on that one. Alright, so now we're going to do that one more time. We have one more example. So that's all one problem, basically. I mean, they're asking us 4 different things, so I guess technically it's 4 problems, but yeah. Excuse me. So here we have one more where we're going to go through that whole process again. Okay. Now we do want to notice here that it says n equals 1. That shouldn't have too much of an impact on what we're doing. We're just going to want to put it, anytime we write a sigma notation down, we'll want to probably just have that 1 written down, but I don't think that's going to make a difference to the math work that we have to do. So here, C is 2. And then step 2 is to use the ratio test. So we're going to take the limit as n approaches infinity, and this is not going to make a difference because we have the absolute value, so we don't really need to worry about that. So we're going to have x minus 2 to the n plus 1 over n plus 1, and then the reciprocal over here is n, and x minus 2 to the n reciprocal of that. Okay, so here we have one more power than we have here, so that means we have one of them. So that's going to be x minus 2, and then that leaves us the limit as n approaches infinity of n over n plus 1. So here's step 3, where we take x minus 2. This is going to be 1. The limit is n approaches infinity is 1. The ratio of the leading coefficients. And so we're going to compare that to 1. So we're going to have negative 1, x minus 2, positive 1. We're going to add 2 to each section. So we're going to get 1 in between 1 and 3. Okay, so we're going to let x equal 1. And here's where we want to make sure we use a 1. Although I don't see that it's going to make any, as far as our work, it's not going to change anything. So we had negative 1 to the n plus 2. And if we let x be 1 right here, we'd have 1 minus 2, which is negative 1. So that's going to be negative 1 to the n power. And that's all over n. Okay. So, do that again. N equals 1 to infinity. So if we add those, we have 2n plus 2, which is even. So that's going to be 1 over n. That diverges by the p-series test. The exponent equals 1. So that's going to be a parenthesis. Then if we let x equal 3, okay, I want to use the same color coding I used on the other one there. So that was all in blue. Alright. So if we let x equal 3 up there, that's going to be positive 1. So that's going to be n equals 1 to infinity of negative 1 to the n plus 2. And here we have 1 to the n over n. So that's just 1. Now here, this is going to alternate, so that converges by the alternating series. So that is going to be a bracket. Okay, so now we're going to take the derivative. Okay, so we have the derivative 1 to infinity, and the negative 1 to the n plus 2 stays there. And then we take the derivative of this, we bring down the n, and x minus 2, and n minus 1. And all of that was over n, so that is going to cancel. Okay, so that leaves us with n equals 1 to infinity of negative 1 to the n plus 2, and x minus 2 to the n minus 1. So it says for derivatives, parentheses stay. So that's going to be a 1, and so we just have to check 3. So let x equal 3. And if we let x equal 3, we get 3 minus 2, which is 1. 1 to whatever power is going to be 1. So that leaves us with this, which means it's going to alternate from negative 1 to 1. And so by the nth term test, that's not approaching 0, so that diverges. And since it diverges, that's going to become a parenthesis on the first derivative. Okay. So then we have the second derivative. So we take the second derivative there. We're going to have n equals 1 to infinity and negative 1. So right here, n plus 2. So we bring that exponent down. We're going to have n minus 1. And then we're going to have x, and we're going to subtract 1 from that exponent, so that's going to be n minus 2. But, again, actually it's a derivative, and so the derivative parentheses stay, and so we would just leave it like that. And we're almost done here, so the last thing we're supposed to do is look at the integral of the function. And so for that, we're going to add 1 to the exponent. So if we add 1, x minus 1, where are we? X minus 2. And if we add, back to the original. So if we add 1 to the exponent, that would be n plus 1, and then divide by the new exponent. So this n is from up here, and this is from the new exponent. Okay, so when we integrate, brackets stay the same. So we have that already. So the question is, what about 1? So we're going to let x equal 1 and see what happens there. So that's going to be n equals 1 to infinity, and that's going to be, if we let x equal 1, that's going to be negative 1. So we're going to have negative 1, and one of these is going to be odd, and one of them is going to be even every time, so that's always going to be a negative 1. And that's going to be over n plus 1. So we can use a direct comparison test. Compare it to negative 1 over n squared, and so it converges by p-series because the exponent squared is greater than 1. 2 is greater than 1. So that means that that becomes a bracket also. And it's about that time. Have a good day.